Hi everybody, welcome to today's seminar. My name is Sudarshan. I'm the current chair of our PELS San Francisco Bay Area chapter. It's been truly a delight to continue this year's webinar/seminar series for us, and I think we have aptly named it Powering Through 2024. I think I can say that I have powered through 2024, so I'm guessing all of you also feel the same. Before we hand over to Dr. Uttam, and I'd just like to tell a few things about our chapter. So our chapter has received notable recognition in recent years. As you can see, we were the Santa Clara Valley Outstanding Chapter Award recipients for 3 years in 17, 22 and 23. We were also the Region 6 Outstanding Chapter Award again for the same years. And we were also the PELS Best Chapter Award for the year 2017. So we would like to continue that tradition of winning all the awards for PELS. So today's talk is on potential and challenges in gallium oxide with next generation power semiconductor tech by Professor Uttam Singisetti from University at Buffalo. So thank you once again, Professor Uttam, for coming all the way from the East Coast to give this talk and support our chapter and with this seminar. Just a few words. We also would like to thank our co-sponsor, which is the Electron Devices chapter from the Santa Clara Valley. And also we would like to thank PELS TC2 for supporting this event. None of these things would have been possible without the support from all of our volunteers and officers. A lot of work goes on in the background, and our officers, do a lot of work in bringing these events and into play. So thank you for all of them. One of the things that we can help you out is if you're not a senior IEEE member, we can definitely assist you with that. It's the highest grade one can apply through a self-nomination or also nominated by others. There are several benefits of being a senior member of the IEEE. You can get your recognition, you'll become eligible for a leadership, and also others that are listed down here. So if you're interested, or if you know anybody who's interested in that, so please give us, please contact us and we can help out as much as possible. These are some of the events that happened this year, a mix of online and in person. We also were co-sponsors with some of the other chapters as well, and I've listed that here, just to sort of give you an idea of what kind of events that we have on a regular basis. So you can all stay tuned for our newsletter, and then you will be able to see what events are coming up and you can attend them. One of the upcoming talks that we are having is on December 10th. It is a hot topic these days, especially in the Valley. It's AI and digitization as enablers of the clean energy transition. So that's the link. It's already been uploaded, and I think as of now you can register for the event. This is going to be an online event. So you know how AI helping power electronics. So anybody who, I think most people might be interested in this. So this is from Dr. Kenman Zhu from KTH in Stockholm. So she will probably go over this topic in detail. Anybody who's interested, please register for the event. This is how you can stay up to date with all the events that are happening. You can follow us on Twitter as well, or X. And these are some of the previous slides and videos that have been uploaded on YouTube. So if you go to our website and go under the resources tab, you will be able to see any of these things and watch the videos. Also, if you'd like to be in the loop of all the great talks and events that are happening, IEEE eGrid delivers all of that info into your inbox twice a month. So you can register on egrid.biz as well to stay up to date with that. Okay. Sorry, but I'll stay on this one. So once again, thank you everybody for taking the time to be here. And now I would like to introduce our speaker. So Dr. Uttam is Singisetti is a professor of electrical engineering at the University of Buffalo. He received his PhD in electrical and computer engineering from University of California, Santa Barbara in 2009. He received his MS degree from Arizona State in 2004 and a bachelor's degree from Indian Institute of Technology in Madras in 2001. He joined the EE department in fall of 2001 at University of Buffalo. He was promoted to be an associate professor in 2017 and became a full professor in 2021. His research interests are in the areas of low power devices for logic and memory. During his PhD, he worked on I think 555B MOSFET devices where he demonstrated all the self-aligned MOSFET technology. His research group was the first to identify the mobility limiting mechanism in gallium oxide. He demonstrated multi-kilovolt class lateral gallium oxide devices and also highest RF performance in gallium oxide devices. He has received many awards. He's the recipient of the Senior Researcher of the Year Award in 2020 and also a UB Exceptional Scholar. He has received a Sustained Achievement Award in 2024. He has authored and co-authored more than 150 publications in peer-reviewed journals and conference proceedings. He is an active member of the IEEE Electron Device Society. He was also chair of the GOX 2023 conference in 2023. And he has served on several journals including the IEEE Transactions on Power Electronics, Scientific Reports and APL Materials. So without further ado, I would like to hand over the stage to Dr. Uttam, and once again thank you so much for taking the time to be here, Dr.
Okay, thanks Johnston for the nice introduction. Again, if you cannot hear, let me know. I can use the mic. I'll try to speak up. And first of all, it's a great honor to be invited by the Power Electronics Society and give a talk here. So my name is Uttam Singisetti. As Sudarshan mentioned, I'm a faculty in the electrical engineering department at Buffalo. Today I'm going to talk about the gallium oxide semiconductor, the next generation power semiconductor, both the opportunities and challenges in the system. Before I start, I would like to acknowledge all the collaborators listed here with whom I've worked on different aspects of the project, and also all the funding agencies over the years who have supported this work. And last but not the least, the students, all the students and postdocs in my group, both current and former students who have carried out all the, most of the work that I'm going to present here. So today I'll talk about gallium oxide. So again, I'll give an introduction to beta gallium oxide. Again, you may not be very familiar with this semiconductor, so I'll spend some time there and then talk about the what are the advantages for technology transfer. Usually, any semiconductor research, there's always a very large lag time. It takes time to develop the technology in the academia and then transfer. When you transfer to industry, there are still some challenges. And there's some particular advantages for this particular material which I would like to discuss. And then next I'll go to the lateral kilovolt class devices that we have developed in our group over the last 7-8 years, and talk about diodes and thermal aspects, and finally summarize. So gallium oxide is ultra widebandgap semiconductor. So I think the community here right now knows about gallium nitride silicon carbide, which we know is a widebandgap semiconductor. Bandgap around 3.3 to 3.4 eV. And we know the advantages of using widebandgap semiconductor over silicon. The higher power, higher voltages, higher power densities. So with the same argument, if you go to gallium oxide, which is a bandgap of 4.8 eV, and which results in a electric field strength of 8 megavolt per centimeter, and as a result of that, you can get low on resistances and high voltages. Right. So this is the whole argument about moving from silicon to the wide bandgap semiconductor. Now, if you use the same argument for ultra wide bandgap semiconductor, you can see that we can have low on resistances and high voltages for this gallium oxide semiconductor. And if you look at the mobility values, it's 200 centimeters per volt second, and that's actually pretty decent mobility. In fact, it's better than silicon carbide channel mobility that you have in the products now, right? But if you compare with gallium nitride, the mobility is not that high. But for very high voltage applications, as we know from this Baliga's figure of merit, it goes as an E critical field per cube, and that's where you see the advantage over say silicon carbide or gallium nitride. Now, of course, this material has some challenges. One of the challenges is the thermal conductivity, which you can see here is 0.24 compared to silicon carbide and gallium nitride, which we know is the challenge always in power semiconductors or power devices. Also, you cannot make shallow acceptors. So, this is only a unipolar device or a mono, you can only do N-type doping. P-type doping is hard because the acceptors are very deep, so they don't ionize. Now, that's a challenge. Now, let's say you were lucky to find a P-type dopant, and then even if you ionize them, the holes will be very heavy. They're extremely heavy, they won't move fast. It's a very, very low mobility, right? But you can see that I actually have said yes here, with the different color, because I will show you some results which show that if you use a hetero-junction, it's a nickel-oxide, gallium oxide. So nickel-oxide is a P-type semiconductor. You can make a hetero-junction, and you can use that to do a lot of the function that you want from a P-type dopant, right? For example, superjunctions, field management, and all that. It can be done by using a hetero-junction, or if you want a hole absorption contact, like, if you have avalancing, the holes are created, you want to capture the hole, you can make a hetero-junction, right? So that I think is not a challenge anymore. However, the holes, they don't have too much mobility, so they won't provide any extra current. You won't have this IGBT where you get extra conduction from the holes. That will not be possible in this gallium oxide. Now, there's of course other competing technologies or competing widebandgap, ultra-widebandgap semiconductors. One is the diamond and aluminum nitride. Now, if you go back to your physics, semiconductor physics or solid-state physics, you know that the only difference between an insulator and a semiconductor is actually doping, right? If you cannot dope it, it's just an insulator, right? And it has to be shallow dopant. Gallium oxide is lucky, that's all I would say, lucky to have shallow dopants. There are germanium, tin, and silicon, and the dopant ionization is 30. So before I go to the talk, I just want to also give you a little bit of the current status of the gallium oxide technology. I would say, it's using the RPI or DOE notation. It's currently TRL3, MRL3, right? Technology readiness level 3, manufacturing readiness level 3. I would say most of the work has been done in labs and universities. Single devices have been shown to very high currents, high voltages, high figures of merit, but it's not in production, right? Of course, the ME Commons from the CHIPS Act has been trying to push some of the technologies to the next TRL level. I think they announced one project for gallium oxide high voltage power switches. Again, people who have worked on gallium nitride, silicon carbide, I would say I was a student, I worked on gallium nitride. This is somewhat like 2010, 2015 of that timeline of gallium nitride when people are trying to commercialize. And I remember a lot of silicon people are asking so many questions. What about dislocations? What about avalanching and all that? So I see the similar thing when I talk about gallium oxide. So there's still some room for improvement there. But I think I would say compared to other semiconductor, this progress on gallium oxide has been very rapid, actually, compared to the silicon carbide or gallium nitride time scales. Now, one thing is we are asking, okay, what is the value, right? In academia, we want to work on next generation technology, right? Because industry can do a lot of things well, and we can use the technology to also train students. Silicon carbide, gallium nitride, very mature technologies. So we wanted to see, okay, where does gallium oxide fit in, right? Is there a market or is there a use case where it has advantages that silicon carbide, gallium nitride will find it very hard, or it will take a lot of cost will be high, right? So one application space that we think can make a big impact is the grid level power. right, for transmission. So one example that is shown here is a high voltage DC transmission. This is very well known to be a better transmission technology compared to AC technology. It has lower losses. There are no capacitive impacts, inductive impacts. In fact, it's in California we have wildfires, right? So if you have a DC transmission, it could be underground, and you don't have to shut off the power, right? So you can see some examples here. This is the for the northern Australia. There's a proposal to have solar farm there. There's a desert there, and then you transmit over to Singapore through this ultra high voltage DC transmission. I was just reading this news. I think the Sun cable. I think they got approval for this project, right? Now, as you can see, the other example on the left, in China from one west to east, it's usually done on an intercontinental scale, the power, right? You're talking about megavolt power voltage levels and gigawatt transmission. Now, why is not used on a shorter distances? Because as seen on this plot here, there is a terminal cost, DC terminal cost, which is the cost, right? So after a critical distance, you have a break even, and then it makes sense to use a DC transmission, right? Now, if one of the cost is actually the converter cost. It's not all of it, but some part of the cost is the converter cost, DC converter cost. Now, as in the Silicon Valley, AI boom is happening everywhere you go. You're talking about AI, and it's very well known right now that AI is actually very power hungry. As shown in this plot there, you can see the normal Google search versus AI powered Google search. You're getting 10 times higher power. And in fact, this is a worry for all the tech industries, right? And you probably heard about all the major players, Google, Microsoft, Amazon, each of them making deals with the nuclear power. Right? In the US, at least the nuclear power was gone. But now, if you have a nuclear stock, or a company, at the stock prices are going up. That's because they realize it is going to demand so much power, and they're worried that there might not be enough power, new power sources coming in. Now, if you have this high voltage DC transmission, again, you can do, kind of meet the AI power demand there. Now, what do they use currently, the high voltage DC transmission? They use thyristors. As you see in this plot from the Siemens, there right now they use 8.5 kilovolt. To make a 1 megavolt, you can see here, you do a series stacking, to get the voltage level that you want, and also you want to do the parallel stacking to get the current. So again, we're talking of gigawatts of power, right? It's megavolt times kiloamps of current, a lot of power, right? So what transistor doesn't handle that, so you do a lot of paralleling, series stacking. In fact, when I talked to Professor Yao, who is a power electronics person, she explains to me that all this series parallel stacking actually increases the complexities, right? You just cannot use it. You need to have a sensor. You need to make sure you have current balancing, voltage balancing. You have redundancies for failures. So increasingly, it kind of goes very rapidly. So if you have like a 40 kilovolt switch, right? So when I was a student, gallium nitride in 2010, 2011, if somebody had asked that can you make a 40 kilovolt MOSFET, I would have said no way. In fact, I remember talking to a power person. We had some discussions, and he was saying, "Okay, can you make, 50 kilovolt device?" I said, "No, that's usually it doesn't happen. Maybe a maximum 10 kilovolt, right?" But right now, you can imagine, based on what we know so far, you can actually make a 40 kilovolt. I mean, it's reasonable to say, okay, this can happen, right? So again, if you're using the Baliga's figure of merit, if you use a triangular field, right, using an 8 megavolt per centimeter as the peak field. If you want 40 kilovolt, you need like a 100 micron drift layer, right? 100 micron drift layer, again, if you are a growth person, you would know that that's reasonable. You can grow 100 micron drift layer. I mean, reasonable, I would say, right? It's still very hard to grow 100 micron thick drift layers, and you have to grow very high quality material, right? But if you want to do it with the silicon carbide or gallium nitride, it will be 500 micron, right? Or 800 micron, right? So clearly you can see that with this ultra widebandgap semiconductor with high field strength, you could imagine maybe 20 to 40 kilovolt switches, and that would definitely reduce the number of switches and reduce the complexity, right? So that's one possible application space where gallium oxide can make an impact. And the other area that we were investigating is for radiation hard electronics. This is for space applications. There's a lot of effort from NASA, even private enterprise for lunar missions, Mars missions. They want to do these missions. It's there in their plan in 5 to 10 years. Now, you want radiation hardening. Of course, when you have electronics go out in space, they do provide shielding, right? But the main failure mode, or at least they want protection, is called single event failure, which is basically if a lucky ion passes through all the shield and also hits the critical spot, right? It's a very low probability event, but if it happens, it can fail, right? So you can see usually what they do is they talk about LET, which has some mass of the material taken into account. You can say electron hole pairs per micron is 1/EG. So if you go to higher band gap, you get less electron hole pairs, which makes sense. But it's only linear dependence, so it's not a big advantage going from say gallium nitride to gallium oxide. But what happens is once you create electron hole pair, you can see here, this is under the high field region. You create electron hole pairs, those will ionize again and break down, right? Now the advantage comes here that if you have an ultra wideband gap semiconductor, you create less electron hole pairs and which have less chance of ionizing, right? So that's one particular space where it can operate. In fact, we have done some simulations. Again, these are TCAD simulations. You can see the device on the left there. I will describe the IV characteristic later. But in the middle, you can see that when the ion strikes, you have a big spike of current. It's a device in the off state. When you strike the ion device, current increases rapidly, and then eventually you can see it comes down, right? So if it comes down to the background level, then there's no failure, right? On the right side, you can see there are some which says SEB, single event burnout. Those simulations, the current does not come back down; it just stays up. This is kind of avalanching; it just locks in there, right? Those are failures. Now, what was interesting here was that you can see the insert there on the top there, the temperature, right? Temperature rise, comes down again. So whenever there's a failure, you can have an electrical failure, you can have thermal failure or electrothermal failure, right? Usually in a power semiconductor. Surprisingly, it did not fail thermally, right? So this particular example here, when you look at the thermal behavior, it did not fail thermally actually. It actually just electrical failure, right? Which is kind of counterintuitive, right? Because gallium oxide has low thermal conductivity, doesn't make sense. But if you think about it, what is happening is that for the same energy of ion striking, you're creating less electron hole pairs, right? You're creating less energy compared to say silicon or silicon carbide. As a result, it's not failing thermally. You're not heating up much, right? So if you see the energy here, it's 0.1 picojoule in the maximum case, which is actually very low compared to say silicon carbide, which is in the nanojoule case, right? So you're creating very low number of electron hole pairs. As a result, you're able to tolerate thermally, right? So this is another example of gallium oxide where it could make an impact. So there are some cases where you may provide advantage over say gallium nitride or silicon carbide. Okay. So now I want to switch and talk about what are the advantages for technology transfer, right? So those are just some simulation or materials property advantages. Now, beta gallium oxide is actually has gallium oxide has 5 phases. Chemistry here, beta phase is the most stable phase. Okay? I think people who may or may not know silicon carbide has 100 phases actually. So that should not be should not be a cause of concern, I would say. But this is the most stable phase. It's a monoclinic crystal again. If you recall your chemistry, you know a little bit on the crystal symmetry. It is anisotropic, so I would say for this audience, just don't worry about it. It has some impact on say contacts and other chemical processes. But the electrons are completely isotropic, right? So if you look at mobility, whereas in all directions, it's almost same, right? So you just don't have to worry about that. Luckily, otherwise, the modeling gets a little bit more complex. And you see in the center here, it's a 4-inch substrate, and that's actually unique for gallium oxide compared to other semiconductors where substrate technology was always lagging behind, epitaxial layer, right? So here, the substrate was mature before people started doing the device fabrication, right? Now on the right you see that you can have very high dopant control. This is showing 10/17, but there are recent results where you can go to 5e15 doping, right? Very low doping. You want very low doping for your drift layers, 20, 30 kilovolts. You need to have very low doping, otherwise you break down the pore, right? And you want high doping because you want to make contacts, good contacts, right? Because the growth is on the substrate, it's highest quality, and actually that's the reason why, as I was saying, the rate of progress of gallium oxide has been extraordinary compared to previous generation. That's because of this reason, right? Because you have substrates, so people are able to grow high quality material, right? So that will have an advantage for commercialization. I think if you know the silicon carbide and gallium nitride story is substrate cost. I think even now a substrate is substantial cost for silicon carbide, right? And that's the reason Tesla still costs pretty high, expensive, right? I know California has very high penetration of electric cars, but when I look outside from my hotel room, I could see a lot of them are still gas cars, right? Because the cost is still high, right? So this, this technology, if you scale, potentially can be low cost actually. Other thing, the material quality is very good. What I'm showing here is that the calculated mobilities are very close to theoretical mobilities, right? So theoretical limits have been reached. The NA, you can see 10 per 14 per centimeter cube. That's very good compared to say, saying that it's only 10 years, 10 to 40 years research has been done. Diamond is nowhere there, and ALN is probably nowhere there, right? So those are the key advantages for high voltage devices. On the right, it's showing 10,000 mobility at low temperature. Low temperature doesn't, it's not relevant for a room temperature application, but the high mobility, which is the highest for any ultra wide bandgap or wide bandgap semiconductor, kind of shows the cleanliness of the material, right? It's very clean material, which is what you want for high voltage applications. This is showing that gate dielectrics, if you want to make a MOSFET, you need a good dielectric. This is showing that we have good gate dielectrics, SiO2. You can see in the center here, the band offset is 3.6. Ideally, you want E-mode device, and then this will give you a good E-mode device. There are other dielectrics, aluminum oxide, hafnium have been demonstrated. Again, they're also pretty good. Okay, so we have good material, epitaxial material, good doping control. We have good dielectrics. That's all you can go. You can make a MOSFET, right? So the first, so now I'm going to switch to talk about the work done in our group over the last few years. So the first device we made is, you can see in the center there, it's a standard textbook kind of a device. Silicon dioxide gate dielectric, source and drain were done by spin-on dopant, and then you can see that on the bottom left there, you get a good gate modulation. Breakdown was 382 volts. On-off ratio is pretty good at 10/8. And these devices were actually breaking down, close to 400 volts. And you can see it's decreasing the temperature. Now the student, when he was measuring this is our manual probe station. When it breaks down, it could actually smell the ozone coming out, right? You could see the spark and coming out. So he said, okay, this is air arcing, it's not device breaking. This is kind of interesting. And then he did some modeling, and you can see on the left here, look at the air breakdown curves, use the dimensions we use. You got 384 volts, you got 382 volts. I'm surprised such a coincidence of the value, but clearly air breakdown was happening, right? So then we move to a field plate design. You can see here what we do is we put a thick field plate. Again, it's a well-known technique in gallium nitride. So the field will move here, as you see in the center figure there, under the field plate edge, and then also on top. So we use fluorinated dielectric liquid to measure the breakdown. And then here you can see on the figure on the left, you can see the IVs of the device. On the center, you can see when you use fluorinate, the breakdown is 2 kilovolts, right? So this is the first time we showed a multi-kilovolt device. And I think this kind of gave a lot of interest for people to do, look at gallium oxide as a, high kilovolt device. Gallium nitride after so many years, I would say, 1.2 kilovolt device is still, I think maybe it's just coming out as a commercially, right? So you can see it's very hard, this high voltage, but this was very easy, I would say. People have made a lot of progress in this high voltage devices. You can see here in the air, the breakdown is constant. Fluorinate, you got 2 kilovolt castor oil. You went to the supermarket, bought castor oil, and you can see it's scaling with the environment you're using, right? So it's breaking outside the device. So you can see the on resistance was poor compared to previous generation. We had some difficulty in the SOG doping. Then we switched to a different process where we start with the N plus layer, as you can see here in the center there. So we start with the N plus layer, the dark blue layer here by MBE, and then we etch away the N plus layer by RIE, and then you form the device, which is same as the previous generation device. Only difference is that how is the N plus layer formed, right? Previously we were doing spin-on doping, you spin coat it, and then you diffuse it by annealing. Here we start the N plus layer and then remove it where you don't want it. And I just want to say that ion implantation also works pretty good. People have shown ion implantation to make N plus layers. That also works pretty well in gallium oxide. It's very stable, so you can anneal high temperatures. So you can see again on the left here, the on resistance is improved. On the middle curve, on-off ratio again very good. Good depletion mode device, and this was very, we use small pieces but very well behaved. Good uniformity across the whole wafer. So figure on the left is showing the temperature dependence IV. Interesting thing to note is you can see the on resistance is not changing with the temperature at all. It's almost constant, almost zero coefficient, right? You can see it's ultra widebandgap semiconductor, so even at 130 degrees Celsius, we've got good on-off ratio. So this is, the on resistance not changing is a little bit interesting interplay. As you go to high temperature, the mobility drops, the contact resistance improves in the widebandgap semiconductor, so the kind of balance is there. You kind of get a constant resistance with temperature. So again, it's a different process. We still got the 2 kilovolt, you see in the center on the left. When you go to high temperature, the breakdown decreases. You can see here, breakdown decreasing temperature, right? So which is a signature that it's breaking outside the device, because if it breaks in the channel, if you go to high temperature, there are more phonons, electrons scatter, they want to ionize, the breakdown should increase, right? And that's what people see in supercarbide. So here we're seeing decreasing or breakdown, which is suggesting it's breaking outside the channel. And again, the student case, and it's a very good student I had. He was okay. Why was it 2 kV? What should be the theoretical breakdown, right? So on the left, you can see he did simulations for the peak field 1 to 5 kilovolt. Again, if you believe 8 megavolt per centimeter as the highest field, it should actually, that particular device should have given him 5 kilovolt, but it's giving 2 kilovolt. And he was saying, why is it 2 kilovolt? And what you can see is that in the middle figure here, the blue lines, the high field regions, they actually go outside the gate house, right? So they go pretty out, I guess several microns into the air or fluorinate. So most likely the fluorinate is breaking down, not the device. So how do you overcome that? You just cap it with some high field strength material. You can see here, you use SU8, which is actually photoresist, right? It's actually 4.4 megavolt per centimeter, which is higher than silicon carbide or gallium nitride field strength, right? It's surprising that it's just a polymer.
But isn't it kind of defects, lots of defects in SU8, or is it?
It's outside the device, so it doesn't matter. I don't think there's defects. I mean, it is photoresist, so they use it in MEMS kind of thing. I guess like coating material, packaging material.
It's almost like an epoxy.
Yeah, that's the right word, epoxy. Yeah, kind of thing, right? Very high field strength, surprisingly very high field strength, right? And you can see, you can just open up, right? You could also cap it with something else, silicon dioxide, silicon nitride, that should also work, right? So again, on the left, you can see device on resistance. Still, again, a problem. Every time we change something, the on resistance go bad. But I'll come back to that later. But if you see the middle figure here, the blue points, we take the wafer or a piece or coupon, 5 millimeter. We fab the device. Once we finish up, we measure the breakdown, right, and go back to the SU8 process. Come back and measure second row of devices, right? And you can see that from blue to red, right, there's a big change in the breakdown voltage. And you can see here, clearly here, this is before you did any SU8, and then after you add SU8, there's a big boost in the breakdown voltage, clearly showing that, you need to manage the fields on the lateral MOSFETs, right, at the top level. And we, in fact, verified this a couple of times in the paper. We have actually 2 devices stored because we were surprised that this is a big enhancement. And in fact, it's true. After this, a lot of groups started using this, even for gallium nitride devices, and they have seen improvements in the breakdown voltage. The on resistance, you can see that what happens is the N plus layer, when you do RIE here, if you're not careful, you can damage this channel layer, increase the resistance. You can see on the red line there, microamps, because of RIE, the current has dropped. But you go back, you anneal the device in a ultra high vacuum, and then this recovers. You can see the blue line on the left, the currents have gone up. In the center figure, you can see the resistance has improved there. Now here you can see that these are two different sets. The previous generation, the gray triangles, and you can constantly see improvement in the breakdown voltage, resistance here. Right? Now what about the breakdown? So we improve the resistance. Is the breakdown same? Yes, it is same. You can see on the left here, different breakdown voltages. The center figure again explains that, the gray triangles, the previous generation, and the blue ones, blue and red, were the new one with the annealing. You can see they're all similar. Right? So we're able to recover the resistance, but not degrade the breakdown voltage. Right? Usually, what happens when you try to do one, the other one goes bad. We also measured 4.4 kilovolt MESFET device. This is by Sriram Krishnamurthy's group, where they use the regrowth of the source drain regions instead of the RIE, so they get good on resistance also. So just the status, I would say that again their group has shown that we can actually get 1 gigawatt per centimeter square of figure of merit for a single device. Again, it's very impressive, as you see on this chart here. People have shown 10 kilovolt devices using lateral MOSFETs in gallium oxide. Finally, the last part, I'll talk about diodes and thermal aspects. So in the gallium oxide, first the MB, they could grow thin layers. So a lot of lateral devices that I discussed, right, they came first. The vertical devices, they came later because they have to go thick epi, as you see in the middle layer there, 10 micron epi you have to grow. So this is a diode. It's a standard feed plate design again. Nothing too fancy here. We were able to get one kilovolt. This was 2019, pretty early, and also the 1 kilovolt without any dependence on the area. Typically, when you say very new technology, there's always variation in the size of the device. The breakdown is lower for a smaller or lower for a large area versus a small area. You can see that it is more consistent here. People have made rapid progress in the, as I will show later. And then some quick reverse recovery tests. 500 milliamp device, not very high. This is showing gallium oxide versus silicon. You can see that there is no reverse recovery, right? Because there are no holes here. And silicon, similarly related device. You can see this whole recovery time there. You can also do the rectification up to 2 megahertz, which is I think limited by our instrumentation at that point. Again, Schottky diodes, they're pretty good. They're fast and they can block current pretty well. So some of other work from other groups. This is using nickel oxide. This is what I mentioned. Nickel oxide is actually a P-type oxide. It's a 3.2 or 3.4 EV. Holes are not very fast, but there are holes, right, which conduct. And you can see on the left here, it's a 10 kilovolt nickel-oxide, gallium oxide device published. And you can see on the center plot here, it's in fact beating silicon carbide. It's reaching the gallium oxide line there, right? This is a single device from single group, but at least shows that you can actually read on a single device, you can achieve those very high figure of merits. This is work from Yuhao Zhang and Virginia Tech, using nickel oxide for the field management, as you can see on top here. And they're able to get 3 kilovolt. Again, if you translate to megavolt per centimeter, the left one is the 10 megavolt per centimeter, right one is around 3 megavolt per centimeter. Right? Those are average fields, not peak fields. So very impressive in terms of the field strength and high voltages. And we believe the same thing will get translated into the high voltage vertical devices. You can maintain this very high field strength and high voltages. Another area that actually came out from gallium oxide, it came out from Ohio State University, Professor Rajan's group, is using extreme K or barium titanate for field management. This actually came from the need to manage fields in very high breakdown devices, and this is showing a lateral device using barium titanate for field management, and you can see that they're able to achieve, single devices, you're beating silicon carbide numbers, right? So again, what I was trying to show is that TL level 3 single devices have been demonstrated conceptually, experimentally, sorry, and then they do exceed the silicon carbide performance. Large area substrates available. You can see the middle figure here. This is from Noble Crystal 50 amp diode. Again, you can make very large current devices. You're talking about grid scale of power electronics. You want large area devices. On the left, it's a 2.5 amp device. Again, in our group, we still have made only small devices. We're trying to make larger ones now. So we can do some switching tests carefully. But that was the highest current device at least I could find reported for gallium oxide, right? Diodes, again, they've made rapid progress, 50 amps, 3 kilovolts, 10 kilovolts. So again, pretty impressive numbers there. So coming to thermal aspects, I mean, this is one of the biggest things for gallium oxide. Everyone asks, okay, what about thermal? Well, it's going to be a problem, right? So I think this community knows very well because of power electronics engineers. You work on device, you make sure that the thermal junction temperature is not too high. But just to, I would say, recap, I think thermal failures are different levels of thermal failure, and a lot of the knowledge actually came from silicon, because silicon was the dominant in power electronics. What is the maximum temperature of operation? First thing is junction failure at high temperatures. So silicon, you always use pH junctions to block, isolate devices. Now, if you go to 300 degrees Celsius, the pH junction fails. So okay, we cannot use it. That's only junction failure, right? Which doesn't happen for ultra-widebandgap semiconductor. The second is thermal runaway. Again, this is from my class for the analog layout design. We know that the BJTs, if your temperature increases, the VBE on decreases, and then one finger, and then that will draw even more current. Right? Again, you get more heating. The VBE decreases. You get a positive feedback. You get a hot spot. And failure. And this is very well known in the analog layout. Please put the ballast resistors in between fingers, right? Thermal runaway is if you have a positive feedback, right? MOSFETs usually don't have positive feedback because there's a good high temperature, the resistance drops, right? The third reason is actually this is from a data sheet. I didn't want to put a name there, but I think it's every device will have that widebandgap device. You can see 25 degrees Celsius. 150 degrees Celsius, how much it shifts, right? So if you have a 250 amp device, and then if the junction is too high, then it's 100 amp device, right? So that's another reason because your device rating is changing, right? That's the third mode, and the fourth one is the reliability of this. High temperature reliability could be issue, right? So those are the things that why we have a maximum junction temperature. And I'm trying to say gallium oxide, the max junction temperature could be high, right? On paper it could be high, right? Junction does not fail because it's an ultra-widebandgap semiconductor, right? Now coming to the thermal runaway, you can see that there are two different devices. The first one I showed previously, you see the resistance is almost constant, right? The second figure is a different device. You can see 300 degrees Celsius, 250 degrees, 25 degrees Celsius, same resistance, right? Resistance does not change. In fact, it goes slightly above, right? Slightly positive resistance as you go to high temperature, and that's what we want. Then there won't be thermal runaway, right? And it doesn't have this rapid, drop, right? So that also is unique in the sense because of the mobility is phonon limited, already phonon limited mobility, so it's already low, and as you go to high temperature, it's not dropping a lot, and then we get some enhancement from the contact resistance dropping. As a result, we get like a slight positive, right? In a way, ideal, what we want out of a MOSFET character. It just happens to be like that, right? The third thing I would say is that of course, we care about dissipated power, and if you increase this, you get the total power high. So delta T is the junction temperature, right? I was saying this could be high, right? Now this thermal resistance, junction to case, case to substrate, and ambient, right? So this could be high in gallium oxide because we have a low thermal conductivity. But if you do careful packaging, so this work on the left from Zhang's groups in Virginia Tech, they did double-sided cooling and they measured experimentally the junction resistance, and you can see it's 0.5 Kelvin per watt, surprisingly low compared to some. These are commercial devices, same rating, same current rating, right? Same current rating. It's actually lower, experimental measure. Of course, this is double-sided cooling, right? And this is from, I think, Transform. They were doing GaN on sapphire, 0.8, 0.5, right? So it's not surprising, it looks like if you do careful management, thermal resistance is not bad, right? I think what works out in the favor is, I guess, if you go to larger currents, you have larger areas, the area gives you low resistance, right? I would say, enough work has been there published that it's not failing thermally. Another work, this is from China, did single side cooling. They did thin down the wafer and did the top side cooling. And you can see these devices can have high surge capacity, right? Thermal failure is, basically does it fail any number of ways. Thermally, surge, you cannot take the surge current, right? It actually can take the surge current very easily. Again, I guess there you got 1.48, which is same as silicon carbide commercial devices, right? And similar to GaN on sapphire. I think I was reading the Transform paper. They were also, I think, coming out 1.2 kilovolt device, which is on a sapphire, not on silicon, right? So I would say, there are a lot of techniques. There's a diamond overcoating, double-side cooling. I think if thermal is, if you need a solution, I think then we will find a solution for the thermal. But that's what I would like to say here. In avalanching, again, nickel-oxide, gallium oxide, there are two groups. You can see on the left here, power electronics, people, you guys usually like this test, right? UIS, unclamped inductive switching test. This is the test you do, right? And they have done the test, and it actually, succeeds. You can see on the left, right? In this particular, I think they said they did 10,000 times, right? Which is still not enough for, I would say, for selling a product. But surprisingly, they all maintain this avalanching behavior, even though nickel oxide, I would say the mechanism still is not very well known, but at least it's passing the test that you like, you want to do, right?
Yeah, better than GaN.
Yeah. So this is, if you want, the thermal test, the surge capacity test, some of the tests. Okay, it's not very exhaustive, but whatever people have done is still showing, it's not failing thermally at least, right? You're not seeing the failures that we were expecting. Let me just skip this. The other thing I would say is that the gallium oxide transport models, the physics also is very well developed, semiconductor physics. You can see on the left, this is work from our group. where I've talked about the anisotropy. It's very low, small anisotropy. You can see there 148, 122. In the center is actually experimental anisotropy. You can see the very small anisotropy. You can see, you can predict that, right? So I'm saying the models are there. When you go to a product, usually you want very good models so that you could make device design quickly. On the right side, it's ionization coefficient. We have all these parameters have been developed, calibrated with experiments. So what I would say is that thermal have been shown. If you make a TCAD device, if it works, you can actually make it. You can actually fabricate it. That's what I would say for gallium oxide. Circuits models have not been developed yet. I think that will be good. So with that, I'll conclude here, and then maybe I'll say a few things. So again, 10 kilovolt devices have been demonstrated. FETs have been demonstrated. Thermal avalancing has been demonstrated. Thermal robustness has been demonstrated. Again, all in academic labs, I would say, right? But the challenges that we thought will be the showstoppers, at least have not stopped it yet, right? Now coming to thermal, what I would say is that we're talking about grid electronics, right? Usually large area, right? So area is always a benefit in terms of thermal conductivity because it reduces the resistance. I would like to talk to the student to give an example of the solar cells, right? Silicon solar cells are not the most efficient, right? If you want to go to best performance, you will go to 3.5. But silicon solar cells are widely used right now, right? The cost of silicon power, solar cell power is lower than gas, right? Now, of course, if you want to do a satellite, you don't use a silicon solar cell, you do 3.5 solar cell because your area constraint, right? So same thing here. I think if it's a large area device, area is giving you the conductivity, right? And also grid level power electronics, they already have the cooling system in place. It's not like you are trying to go in a system where there is no cooling. They actually already have a lot of cooling with the current technology. So you're not putting added extra cost there. So in fact, you might reduce the cooling requirement, right? I think I was reading today. So I think the progress has been great. I think at this stage, there are a couple of startup companies I know who are trying to commercialize. Hopefully, if a diode or something comes out commercially, that's the best case scenario. And I think the power electronics community can look at the things and see if there's any benefit in terms of performance. Okay. So with that, I'll stop and take any questions you may have.
Thank you so much for the talk.
Thank you very much.
It was great having you here, and I'm sure everybody loved your conversation. And we got to learn so many new things.
Yeah. So again, just you can always search my name, or there's my email address. Yeah, somewhere there. Yeah. Please reach out to me. I don't have cards, but you can email me.
Yeah, and we'll upload the video once it's done on our website, and also the slides.
I will. Let me send you a cleaner. Just
Yeah.
in case there's something.
Yes, after you share. So
Yeah.
once again, thank you everybody for taking the time and coming out here, and please stay tuned for more webinars and seminars from us. And very nice to have you, Dr. Uttam. Thank you.
Thank you.